Hi everyone, I'm Francis Gorman. This is the Entropy Podcast, and I'm delighted to be joined by Bob Oates, Associate Director with Cambridge Consultants. How are you, Bob?
I'm very well, thanks, Francis. Thanks for having me on board.
Great to have you as our very first guest on the show. It's been a bit of a roller coaster year so far in the technology and political world. We've had a 500 billion investment announcement in AI. We've had 2 trillion wiped off the stock exchange. Meta has stopped doing fact checking, and Google are changing names and maps. And the Entropy Podcast has dropped. So we're only a good few weeks in. So that's all good stuff, I suppose.
All massive events in security, all of them.
So, Bob, we're going to talk a little bit about security engineering and the interlock with safety engineering. I know you've got some really good examples in this field, and it's a topic that probably doesn't get discussed a lot in terms of the wider technology landscape and how we knit together disparate technologies for a singular outcome. You had some really interesting experience with Rolls Royce and Switzer in your past, and I think maybe we could talk a little bit about that project, if that's okay?
Yeah, absolutely. I guess I think it's worthwhile talking a little bit about just safety and security in general, and then I can explain how that plays out in a project, and that's probably a good way of starting that. Safety and security are really different disciplines, but they're rooted in the same objective. We're trying to prevent harm, whether that's accidental or malicious. And to do that, you've got to manage risk in technology. That's it. So they align beautifully, and where they connect really is quality. If you can't do quality, you can't do security, and if you can't do quality, you can't do safety. Because as engineers, your only real lever for controlling risk is to set requirements and say this system shall have a firewall configured in this way, or this system shall have redundancy to stop one failure causing a massive incident. And if you haven't got quality underpinning them, you can't be sure your requirements are going to be delivered. So they're both sort of rooted in this notion of quality delivery. The only real way of connecting them when they work on a project is systems engineering. You've got to take these multiple views on the system so that everyone is communicating, and you can see what design decisions by one set of engineers has the impact it's going to have on everyone else. And for the most part, I would argue safety and security pull in exactly the same direction. There's 2 types of occasion when that isn't the case. It's when they generate churn, and there's sort of rework and redesign, and that can get really expensive very quickly because they push you more around more and more design iterations, sort of pulling in different directions. And occasionally they pull in literally opposite directions. They want just different things out of the system. So yeah, with that in mind, we worked on what is the world's first commercial remotely operated ship, which is a bit of a mouthful.
Pretty cool though.
Yeah, it's really cool. It was
cool project for the CV. Yeah,
it was such a wonderful project as well because everyone was really committed. We had a lot of support. It was long hours and tight time scales and really complex technology, but it is one of the happiest sort of memories I have of being an engineer is working in that project. It was really, really, really great. And we one of the things, because we were delivering this very complex project and it had to be commercial, what that meant was we had to get it regulated. We had to go to the Classification Society and demonstrate that it was safe and secure. We had to go to the flag state. And I always think this is quite an interesting thing, that security doesn't do as much, but safety has really got down, is the generation of, they call it a safety case, which is like an evidence-based argument you've done enough. And I don't think the security community does that as rigorously as they could in certain situations. In this project case, we actually tried to mimic it. We tried to blend them. because when you've got it was a tugboat, which is basically the biggest set of engines you can find loaded into the smallest ship that can hold them. That can do a lot of damage. There's a lot of thrust in those systems. They can pull really big ships. And there's a real benefit to try and make them remotely operated there, because actually, if a big ship gets in trouble, it could pull a tugboat under, and that's dangerous for the people. There's a reason we have this expression: "Worst things happen at sea." So the being at sea is dangerous. So if we can try and reduce people's risk, that's a good thing.
And Bob, when we think about that, so you're talking a pretty big vessel here in the project that we're discussing. You don't have a captain on board the ship. Apparently, it's all remote. How does that work? Like, how does that hang together? Like, that's a pretty big safety concern, or even in terms of a new era of technology meeting, automotive infrastructure and meshing it all together and putting it in water. Like, there must be so many different considerations there in terms of the safety and security aspects, all within a singular program.
Absolutely, and you really, and I should say, we always had a safety crew on board for our trials and testing, because it just wasn't. It wouldn't have been right not to have done sea trials with someone with a big button to be able to say, no, I'm going to take control. And yeah, you're right. There was a lot of complexity to manage. You've got connectivity. If your safety is reliant on being able to communicate between 2 points, then of course your that comms channel becomes a sort of a safety critical component, and that's a challenging thing to do. Your average, your mobile phone provider is not going to sign a contract to say that they will definitely maintain connection all the time. So you've got to think about that. I think the one of the biggest technical challenges actually was this intrinsic connection between the safety and the security. If a highly connected digital system is not secure, how can you possibly say it's safe? Because the safety relies on the integrity of the software and the data and the network behaving in a deterministic, predictable way within bounds. And if you allow a malicious attacker to run riot in that system, your safety argument just falls apart. So that was the really interesting thing for me, was how do we, when those things are so entwined, how do we make sure they work well together? And also, safety wasn't the only set of goals. When you've got a remote ship, there's a lot of intellectual property, there's a lot of interesting code. So while safety is obviously the most important goal, you've got other security concerns that you need to worry about. So
I really want to see your threat model. The architect to me is dying to see all of the components broken down with the.
And we had to do that, and there was a lot of really good systems engineering. I'm a big fan of something called model-based systems engineering, where you have a single coherent model, and people can look at it with different. There's a lot of great tools out there now where you can draw these architectures out, map out the comms system, and it will show you that system in one way if you're a safety engineer and you're used to seeing diagrams of a particular sort, and it'll show you in a different way if you're a security engineer, but you're looking at the same underlying data model, and that's a really powerful tool for that sort of thing. I'm just sort of running through some of the things. Maybe I should give a very specific example that I think is quite a nice thing. So we had a set of very specific conditions that we wanted to avoid, and the safety team, whenever you see safety and security connecting, that usually is how it works. The safety team are really good at identifying horrible things, so that is part of their mindset. And you see it in aerospace as well. So the aerospace standard is a ED202A, and it gives you this flow diagram of how the safety team and the security team are supposed to share information, which is really useful. And it starts with the safety team saying, I don't want this thing to collide with other ships. I don't want it to lose sensors so, when I'm in the middle of the ocean. All of these scenarios. And then it's the security team's job to make sure that they are preventing those undesirable situations from manifesting. So you sort of trace it back.
That's a really interesting concept. The two streams running beside each other. Is there something there we should be looking at in the wider industry view of the world? You're talking about highly regulated systems engineering in terms of ships and planes and drones and stuff that when it goes wrong, it goes really wrong. When we look at other industries, pharma, finance, etc., that dual stream of safety and security and meshing it together, is there a framework in the making there? Is this SABSA 3.0 or something that we potentially could cobble together?
It's not dissimilar to the really core NIST RMF, where you just basically say, you've got to know what you've got. What are your crown jewels? What do you really care about? Because if you try to secure everything to an equal level of rigor, you'll blow through your budget and nothing will end up being properly secure. So how do you prioritize the things that are really valuable to you? And in traditional cyber, we would do that by doing a CIA assessment or something similar and say, what are the impact, the system level, the business level impacts of those failures, and we'd prioritize accordingly. It's just a slight extension when you've got safety involved, where they say, well, here are the sort of the anti-patterns. Here's what I really don't want to happen. Could you? And actually, the safety engineers, of course, they'll also do a lot of analysis about how specific system failures map up to system-wide effects that are undesirable. So, if that bolt wears through, what does that mean for the propulsion system and that sort of thing, and what does that mean for safety? So they're really good at making those maps, and then it's up to you as a security person to go in and say, well, in that big tree of failure mapped to disaster, are there digital components? And what happens if they lose control of those bits of software, or that data isn't where they thought it was? And can I safeguard that? Because those are the really important things, because they're sat in that chain of causality to disaster. And I think that's again, it's not dissimilar to the way traditional security works. It's just a slightly different perspective.
It's like we take the kill chain, add security in with the what we really don't want to happen lens, and we'll wrap around your threat model, and you've got a dual lane approach to something that's really going to give you a fantastic outcome. When the project came together and you stepped away, there must have been an awful sense of accomplishment and pride to see it, taking. I won't say taking flight, because that's the wrong analogy, but setting sail on its maiden voyage.
Yeah, absolutely. And we were, we were a very close-knit team, and it was an amazing day. And we had, as you do, you have these days where you invite various dignitaries to come and see it, and there was a real sense of pride that what we'd achieved in a surprising time scale. And although of course you can't always, as a security person, you're always sort of cursed in some ways that there's no pretty pictures to show people. You can't really go to like a very senior manager or a very senior stakeholder and show them like ones and zeros flowing across the screen and say, I did that. It's really good. You've got to, it's very difficult. The bit of that project I found most interesting was the intrusion detection system. And I would have loved to talk at great length to anybody who'd listen about the design of the intrusion detection system. But it's not for everyone. It was actually a really good example of how safety and security interact, because with intrusion detection systems, you're looking for anomalies. And actually, by design, safety incidents are anomalous. You hope so anyway. You don't want them to be the norm. So if you go purely on anomaly-based detection, you're going to start raising alerts when there's a safety incident. And that's when you want to be bothering the operator the least. You don't want them to be having to manage a genuine incident and then flagging up loads of false positives saying, oh, the network traffic's doing something unusual. So that was a really interesting thing. And of course, practical concerns that you don't get in an office. We had to use fiber optic cable for all the networking. And the reason for that is ships get hit by lightning all the time. And intrusion detection systems touch every other system. So if they get like electrically charged to a high degree, they can damage everything, and that can wipe out the ship. So again, it's another safety concern that you wouldn't necessarily think about if you were just securing an office.
Copper is in big trouble when he lands on the ship. That's fantastic. Yeah, okay. So yeah, hit by lightning out in the sea. Yeah, fries all your systems if you wired wrong. That's just another real gotcha if you don't really think these things through at a macro level. The anomaly piece is fascinating, Bob, in terms of, looking for the different patterns. I think we're in an industry at the moment where everyone is selling capabilities that, will detect, will do a zero trust implementation, will surface all the uglies in your databases and your applications and across your network, etc. But we know as security architects and engineers, unless you know what you're looking for, unless you have high fidelity, security relevant information feeding into your SIEM and your SOC teams, the likelihood that you will discover anything other than having a massive log store is probably very low.
Yeah, and I actually would say it's probably, I know we always like to think we've got the hardest job in the world. But operational technology, it's even worse because a lot of the suppliers of operational technology, they're very small organizations. They're very functionally driven. They want the device just to work, and you want it to work straight out of the box. And I've seen some absolute horror stories. That these beautiful, like it's all ergonomically designed white plastic and blue LEDs, and it's the latest and greatest version of this particular sensor array or whatever it is, and it's running 15-year-old Linux under the hood because that works, and that's always worked. And why would I change it? It's not broken. So trying to change that mindset, and when you plug those things into your network, then obviously you end up with anomalies because they've lost control of their software stack. So they're kicking out packets, and they don't really, because it's a legacy part of the operating system, or even the newest stuff. If they misconfigure it and they're kicking out like IPv6 on your beautiful IPv4 network, that's going to raise some anomalies as well.
You're triggering me now on my IoT concerns, and then when we break down all of these things at a hardware level across a ship, different devices, then you've got to make sure that they're within your boundary of your network, that they're all protected. Somebody that puts a system off the side door that has something in it. When I think about smart meters in the electrical grid at the moment, it keeps me up at night. I want to know, have we got a single circuit in everyone's meter, or have we got multiple different breakdowns in the authentication cycle, and what can push what where, and does it have a back door into my network if it all goes wrong? It's that OT and that IoT problem. It's complex.
I think in especially transport, so maritime aerospace, that I think the advantage is that they tend to be quite rigorously designed. So you know who should be talking to what in advance. And that's one of the things we leveraged. You can draw a map fairly quickly that, you know that the front-facing camera probably shouldn't be sending packets to the engine controller. You can put some really logical, functional parameters into that system definition. Whereas I think with enterprise systems, they do tend to evolve a bit more. People connect devices that maybe they shouldn't, or maybe because the people are under pressure, they've got to deliver, so they connect the latest and greatest system to help them run, and those systems sort of evolve, I think, a lot faster. Whereas certainly in aerospace, you wouldn't change the configuration of the network in field without signing about 80 different legal documents and making sure that you were definitely the person you say you are, and that sort of thing. So it is in some ways we get some bits of that problem are easier, but yeah, it's certainly not plain sailing, if you'll pardon the pun.
I like that one. Yeah, that is definitely that's definitely a pun we can end on. In terms of your wider experience, Bob, and I know I'm following your career on LinkedIn. I can see you're doing lots of warm up talks in the post quantum space and getting into the detail. And I know we've had a couple of conversations in post quantum in the past. And that's a real future challenge. Probably not well understood at the moment. AI is still the predominant player in terms of what everyone wants to talk about, but there's a real risk. And when we see what's happened with DeepSeek coming out of the blue to kind of undermine an entire industry this month, you have to know what else is cooking behind closed doors in the quantum space. Do you want to give some views on where you see cryptography heading for, and some of the gotchas that people may not just understand or realize are coming probably quicker than we can determine, even though there's no defined timeline?
Absolutely, and it's it's another wonderful complex problem. That's what keeps us getting up in the morning. So it connects to the OT. So I will try and talk about how I think it also it connects to the OT world. So in terms of the threat, obviously we've got harvest now, decrypt later. We've got people who are confident enough that they're going to be able to read intercepted traffic, so they're storing it en masse, hoping that they'll be able to read it at some point. And I'm not, it's a pressing threat, but at the same time, we have to balance that quantum computers are slow, and they're always going to be slow. They're not going to be solving the data deluge problem anytime soon. They're really good at computational intensive but low data problems. So quantum computers are going to do amazing things in the future, and we should always focus on this as a really positive technology. It's just that one of the things they're really good at is essentially calculating the private key from a public key, which is a nice, again, low data, high computation problem. So if you bear that in mind, the harvest now decrypt later people have got a really hard job. They're going to have to think very carefully about what they want to decrypt, because it's going to take them, even when they've got the machine, it's going to take them quite a few hours per key to start that decryption process. So I think the people who are most at risk are probably, nation states being targeted by other nation states. That's the reality. But as it gets more common, we do need to worry about the thing that really makes me quite nervous is digital signature-based attacks, forging certificates, and a lot of operational technology, as well as enterprise technology. Your entire security premise is that to stop people executing arbitrary code is that you can use a digital signature to demonstrate that it comes from someone you trust. And if you can run whatever you like on PLC or PowerShell or whatever you want to do, that's obviously a really disruptive problem. And those certificates are not updated very often. We assume that they can have lifetimes of maybe a years, and that gives the attacker lots of time to compute forgery. So that's the one that sort of worries me in the longer term, maybe medium term, let's say. For OT, that's going to be a real problem, because a lot of these operational technology systems are really running on a knife edge. And the new post-quantum cryptography algorithms, they do have different properties. They will need need different types of computation. So they'll introduce latency, because you've got to process potentially. Some of them are faster in actual fact, but it's all very difficult. You have to be aware of what you're introducing into your system, because control systems, latency can actually destabilize them. They'll just stop working. Bandwidth as well, key exchange takes about an extra kilobyte per handshake, which doesn't sound like a lot, but if you're operating at scale and you're doing lots of handshakes, or you've got this tiny network that's really very busy, Yeah, I think people are
You're
going to need
going
to
to
think very
topple your
carefully.
network devices and cause all sorts of intermediate problems for
Yeah,
your business, you know?
it's
Yeah, and
it's the risk of action as well as the risk of inaction. That's the
I think
problem.
that's a really key message. And you know, been spending a lot of time talking about post quantum lately, and you know what it means, and you know, try not to be the fear monger, but also have some realities around it. And I think for a lot of organizations, even understanding what cryptography means to them in terms of their inventory and their visibility and their understanding of all of the above is the first major challenge, you know. And then, you know, you get that visibility and maybe you go, we're not even at today's standards, never mind post quantum. We gotta do some work here, you know, and you've got to bring stakeholders on a journey. So it's discovery, and then it's stakeholder management. Then you've got to get programs of work together. You know, the years to quantum are probably going to catch up on your efforts, you know, at some point. So it's a really nuanced problem. And I think if we go back and we talk about Y2K, a lot of people speak of Y2K like a non-event, but reality was there was a lot of preparation behind the scenes to change programs and systems and different things, that when it came, it was a bit of a non-event. You know, I remember being entirely disappointed when the clocks changed and everything didn't blow up around me. But you know, it's it kind of has some. I see people calling it a time to Q day, which doesn't sit right with me at all. But you know, it's year Q or whatever we're going to talk about. But there's definitely going to come a marketing term, and I think we need to be careful to make sure the realities of the work that needs to be done come true, because regardless of the ability or speed, understanding your cryptographic inventory and where it sits and mapping it all out is something we probably should have everywhere anyway.
And there's a lovely lesson we can learn from safety again, that when you deploy some new technology in a safety system, even if it's a control to make you safer, they have traceability. They can always trace it back to justify, why did I add that extra complexity? What's it giving me? And we need to be able to make that argument about cryptography to our stakeholders, to be able to say, this is the value of the cryptography. This is what it's doing for your organization and helping you reach your goals. Because otherwise you're asking them for investment, and it's very easy to feel like, oh, there's the security team again. There's another pressing threat. Yet another. We've only just dealt with AI. What are you talking about? So I think, yeah, it's really important to be able to articulate the value of that, as well as, of course, knowing where you've actually got cryptography and what you're doing with it.
And then when we tell them when quantum computing meets AI, God knows what's going to happen. We need a whole other budget to deal with that stuff, you know. It's it's definitely plenty of work to do over the next couple of years to keep ahead of things. It's not getting any easier.
No, but again, I noticed that people always talk about the skills shortage in security, and actually there is a skills shortage in safety. That, you know, it's really hard to get people to engage with those disciplines because they look hard, they're scary, there's a lot of responsibility. But it's such a fascinating discipline. People should be told these stories about how amazing the projects you get to work on, and you get to do everything, because you have to have at least a surface level understanding of every bit of your organization, or certainly every bit of the system you're trying to protect, to do it effectively, which means you really do get a great bird's eye view of some really cool stuff. I would encourage anyone to, if you're in security or safety, go and tell whoever will listen about how amazing your career has been, how enriched your career has been for being able to play with this cool tech.
And it is true. I think if I look back on my career today, the amount of amazing projects I've been involved in, and, you know, you kind of forget about them, and on all of the challenges, you know, we had cloud emerged, and that created a whole lot of problems. And, you know, then we had AI just jumped out of nowhere, and then quantum appeared, and, you know, go back even further, and there's all sorts of stuff everywhere. And then when you look on it, that's really where you learn. You fail a lot, and you make plenty of mistakes, and you kind of go, well, I'm a little bit better from that now, even though it hurt a bit at the time. You know, I said some things a couple of years ago that no longer hold weight, like, but it is fascinating. It's funny. I think when I'm back home and I'm talking to people, they still think I'm the security man where I work. You know, I'm standing at a door letting people in and out. Like they don't really get the discipline at all. My wife looks at me. I try to tell her what I'm doing at the day basis, or I can see her eyes glaze over. So it's probably an underappreciated discipline as well when you have a cybersecurity profession or a safety profession. It doesn't sound wonderful when you start talking about application level controls or SQL injection attacks, or, input validation or any of these things. But, when you bring them all together in the picture and then someone gets a nice news story and you can make it sound a bit cooler.
Yeah. And I although I do worry now, you've just said, the things change, your understanding of the technology changes over time. And here we are recording for posterity what we think today. It'll be interesting to come back to this recording in a couple of years and ask ourselves, do I still believe all those things about quantum computing?
We'll just blame AI, Bob. We'll just say we were impersonated. No one can fact check it by then anyway, the way things are going. So it's all good. Look, Bob, thanks very much for talking to me. Thanks very much for taking part in the very first episode. So really appreciate it. And we'll be keeping a close eye in the future. If we survive episode 1, we might have you back in the future to talk again. Fact check this episode, see how we get on.
Well, thank you very much for having me. It's been really fun.
Thanks a million. And have a great evening. Take care.
Cheers.